All right, so now we're going to move into some of my more favorite topics of this chapter. So the first thing we need to figure out, well, there's actually quite a few things we need to figure out here. We need to figure out how the Earth goes from a molten mass to an object that has layers. We also need to figure out where the continent and ocean crust come from. We also need to figure out where the water comes from. We need to figure out where the atmosphere comes from. So we've got a lot of things that we still got to figure out here. So let's see if we can piece this together. So the first thing we can talk about is where the layering structure comes from, right? The crust, mantle, core. And there's actually two theories here that could explain where the layering system comes from. But I will tell you that most scientists prescribe to this first concept, which is the solar nebular theory, or the cold accretion model. Basically, the cold accretion model states, I'll make this easier here for you, right, that we know the Earth started out as a homogeneous mass, right? It accreted materials, which you can see here, that's what all those arrows are, and it was molten. Obviously, as objects collided into it, it started to rotate, right? It's being tugged on by the sun, so it's got rotation. As it rotates, it differentiates. Differentiates is a big word there, but that basically means is separation by density. So as the Earth is spinning, the heavier material is going to sink to the center, whereas the light material is going to come to the outside. Same way that a centrifuge works, right? You put a blood sample in a centrifuge and you spin it, right? And you can separate all the stuff out, right? Same concept. Obviously, the thing here is that the Earth has to be hot in order for that to happen. So the sources of heat, right? Well, we've got accretionary heat from bombardment as objects are colliding with the Earth. Of course, gravitational compression as the material's moving towards the center, it's creating friction, right? So we have some heat there. But by far the main source of heat, which is still the source of heat today, is radioactive decay. As those radioactive minerals that are present in the core are decaying, right? They're giving off heat, just a normal byproduct of every single chemical reaction. So I can tell you that this is the more likely of the two stories as to how the Earth got its layers. But there is a second explanation, and that's called the hot accretion model. The hot accretion model basically says that the Earth kind of formed like a mineral. Okay, so when minerals form, they form by, right, you've got a molecule that's in the center, and then as it grows, it's going to deposit molecules on the outside of that. You're going to get molecules on the outside. So it grows right from the inside outwards, right, as you can kind of see from this poor drawing that I'm making here. So the hot accretion model basically states that the Earth is no different than just a really large mineral, and that basically the core formed first, right, and then the crust formed last. Odds of this actually happening is pretty slim, just because that would be really complicated, but we can't discount it, so that's why we're talking about it. Okay, so we got our layering systems, but what did that first crust look like on our planet? Well, remember, if Earth was originally homogeneous molten mass, it was much hotter at the surface than it is today. So Earth's initial crust was extremely different. Its initial crust had lots of iron and magnesium in it, so definitely very mafic, okay? This original crust is what we call a komatiite. You can see this beautiful green color that it actually has. This is a thin section from a piece of komatiite. And what's interesting is komatiites no longer form today. These are rocks that did form at the surface back in the Archean, but these rocks need a temperature of at least 1100 degrees Celsius to form. So what's pretty neat is seeing komatiites up at the surface during this time tells us that Earth's surface was at least 1100 degrees back in the early Archean. So obviously early Earth was very different than it is today. I know Louisiana gets hot in the summer, but definitely not 1100 degrees hot. Today we have two different kinds of crust, right? We have oceanic crust and continental crust. Hopefully you can figure out where we find those. Our oceanic crust is mainly composed of basalt, whereas our continental crust is formed of the lighter, more buoyant granite. So we need to figure out how we make this switch. How do we go? We need a mechanism that's going to take us from going from komatiite crust to that ocean and continental crust. Well, let's take a look and see what we have. So there's some things that we need to look at to try to figure this out. One thing we can look at is some of the oldest stuff that we have on our planet, and those are zircons. So zircons are a mineral. Most of these minerals form very early on in Earth's history. And our oldest zircon grain that we have is 4.4 billion years old. That's the oldest object that we have on our planet. Now, I want you to pay attention as I say this. This zircon grain comes from a metamorphosed sedimentary rock. Yeah, that doesn't sound like a lot, but there's actually a lot of clues there. So first we have to realize that a zircon grain comes from an igneous rock, right? It's brought up by magma up through lava to the surface, right, where it's exposed. So let's make a drawing here. So we've got the earth, right? We've got our magma carrying that zircon grain, and it comes up to the surface, breaches the surface as lava. We get a lava flow, okay? In that lava flow, we've got our little zircon grain. So that igneous rock cools and solidifies, but now it's exposed to the surface, which means, right, the rain is going to beat down on it, and the wind is going to whip across it. And as that happens, that igneous rock is going to start to erode. As it erodes, it's going to release that zircon grain, and that little grain is going to travel, right, and get transported somewhere, right, of course, in water, right, it's going to get transported. Eventually, it's going to form a sedimentary rock, right, so maybe say in a sandstone, right, so we've got this nice little rock here that we find that zircon grain in. But that sandstone got swept up in a subduction zone. So remember, a subduction zone is where we've got two plates, right? This plate that's sinking beneath it. So our little sandstone here got swept up in a subduction zone. As it got partially subducted, it was exposed to pressures and temperatures, and that's what metamorphosed it. Whew, that's a long history for just this tiny old little grain here that's about the size of the grain of sand. Well, what's important about all of that process? Well, first of all, it's old, 4.4 billion years. But there's one key thing in here that I said that's really important that we hadn't talked about yet, and that's the water. Okay? Anytime you've got a sedimentary rock like this, you've got water. So by seeing this grain at 4.4 billion years old, we know sometime after 4.4 billion years, there was enough solid material on the Earth, and we had processes going on that was releasing water into the atmosphere. So that's definitely pretty important. So this grain is telling us something about the formation of water, the timing of the water. The other important thing that I mentioned, right, is that it was metamorphosed in a subduction zone. Well, subduction is a plate tectonic process. So that's also another key thing that we need to figure out when it started. All right, so how do we make that switch? How do we go from komatiite to continental oceanic crust? Well, your answer is almost always going to be plate tectonics. So with the advent of plate tectonics, we're going to make this switch. So I want you to envision we have these pieces of komatiite crust, right, that are floating around. The odds of two komatiite crusts hitting each other is pretty high. As they collide, just like what the ocean crust is today, one's going to subduct below the other. Now, what's important about this is we've got to remember what elements we find in there. So remember, we know it's mafic. Because it's mafic, it's going to have iron and magnesium. But remember, the other two common elements are oxygen and silica. And of course, wherever you find iron, you're going to find oxygen. So we also find smaller amounts of oxygen and silica in there. Why is that important? Well, as this plate subducts, remember, it's experiencing a lot of friction right here. That friction is going to heat up the top portion of this downgoing plate. as it heats up, these rocks are going to melt. Now, out of these two groups, right, the mafic group and the felsic group, which of those two is going to have the lower melting point? Hopefully you said the felsic group, because that is the correct answer. So, as this material starts to melt, your oxygen and silica minerals are going to be released up to the surface. So, all of that lava that's going to come out of these volcanoes, don't ask why it's a green volcano, but all this lava that's going to come out of these volcanoes here is going to be, it's going to have a lot of felsic material in it. So now we're basically drowning out our komatiite with felsic material, and that's starting to give us that switch to the continental crust. Remember, the continental crust is felsic. So with the advent of plate tectonics, this is where we start to make that initial switch. The oldest felsic rocks we have on our planet are 4.4 billion years old. You can find those up in Canada. So, right, now we can check one big thing off our list. We know when plate tectonics started. All right, next thing we need to figure out is the water. So one major product we want to look for to see water is a paleosol. Okay, so the word paleo just means old. The word sol means soil. So an old soil zone. Soil is formed through erosion, right? So as water beats down on the rocks, we're going to start to form soil. We find our oldest soil zone at 3.46 billion years old in Australia. So where we see that, right, that tells us we have enough water on our planet that's sitting and eroding this material, right, that it can create that old soil zone. However, don't forget, our oldest zircon grain at 4.4 billion years old was released by water sometime after that. Okay? So we know we start to really collect water somewhere around 4.4 billion years, but we have enough on our planet by 3.46 billion years that we're collecting a soil zone. So in the next section, we're going to figure out where that water comes from.